Welcome everyone. Let us continue on our discussion about the mixture densities. Last class we ended the last class by discussing the need to have uh, a model that can approximate any continuous density to arbitrary closeness, and we saw that a Gaussian mixture model is one such choice that can approximate any density to arbitrary closeness. So in today's lectures we will look at an iterative algorithm for maximizing the likelihood for such mixture densities, right, because remember that our goal is to estimate the parameters of an underlying model by minimizing the KL divergence, which is equivalent to maximizing the likelihood function, okay, of log likelihood of that particular model under the observed data points. And the way we did it for some primitive densities was to write down the likelihood, take the derivative of it and find out the optimal parameters. But for the cases of densities such as mixture densities, this optimization problem cannot be tractably solved, in the sense that you cannot differentiate that, and the terms that you need will not group themselves up. So you need to resort to an iterative algorithm, which we call the expectation. One such iterative algorithms is what is called as expectation maximization algorithm. We will look at that algorithm today. So that is the objective for today. So let us recall that a mixture density model p theta of the variable v. This is given by the sum of what is the notation, theta jv, where p theta j is a density function and alpha j's are all bounded between 0 and 1 and they sum to 1. This is the definition of a mixture density in general. Now a special case of this is what is called as a Gaussian mixture model, where the constituent densities p theta j are all Gaussian densities with parameters mu j and sigma j. So we have m number of mixtures. So this capital M is what is called as the number of mixtures or number of modes. So how many densities are you combining? So please note that we are saying that our density function is a linear combination or a convex combination of m other density functions. So that is the model that we are looking at, okay. And I also told you that the Gaussian mixture model or Gaussian mixture density is a universal density approximator, in the sense that it can approximate any continuous density to arbitrary closeness. So what is the criteria? I mean, the closer an approximation that you need, the more the number of mixtures that you should choose. This is a hyperparameter. I mean, this is a model choice. It is an engineering choice that the designer has to make. What should be the number of mixtures that we would look at? So, but if you have enough number of mixtures, then you can approximate any density to arbitrary closeness. Now this is a theorem that is known. For the want of time, I will not prove that theorem. So this is Gaussian density. Now let us look at parameter estimation or ML estimation, maximum likelihood estimation for mixture densities. For mixtures. So recall that we wanted our parameter set theta. Okay, so by the way, I'll mention it. So theta was taken to be the maximizer of the likelihood function. What is the likelihood function? Take the log of the sum of log of the likelihood evaluated at all data points, that is our likelihood function, right. This is what we wanted. So, in the case of a mixture density, the set of theta, so specifically for the Gaussian mixtures, right, what are the parameters that we are considering? They are all alphas, and we have how many of them? We have m of them, right. So, there are alpha j's and we have mu j's, sigma j's. So, these are the set of parameters that we need to estimate. So, for j is 1 through m. So, for each of the Gaussian we have the corresponding means and the variances, and we have this alphas which are also model parameters that we would estimate. Basically, this is the mu's and sigmas are telling you what should be the spread and the centering of individual Gaussians, and alphas are telling you how each of these individual Gaussians should be combined such that you get the underlying density estimated. So, that is also a parameter that needs to be estimated along with the other parameters. So, we have alphas, and note that all alphas are scalars, mu and sigmas are vectors and matrices. So, mu is a vector of dimension d and the sigma is a matrix of dimension d by d, and alphas are all scalars. Okay. So, these are the number of parameters that we should estimate. Now, what happens is that for the mixture model, if you consider the log likelihood, so log p theta of vi is given by log so this is the form that we end up getting for the case of a mixture density. Now, observe what is happening here. All the while we had sum of log term, actually there is another. So, if you take a sum here over I, so please note that we get two sums here. One, the outer summation is over the data points that we have, the inner summation is over the number of Gaussian components or mixtures. These are very different. Now, all the while when we were doing maximum likelihood estimation with primitive densities, we had this form where we had log of some density, and this density, if you can represent that as an exponential family of density, the logarithm and the exponentiation will get cancelled off, and you get sum of a few terms that could be differentiated. Here, if you look at the structure, these Gaussian densities have the exponentiation, but you have a summation inside the logarithm. So, that means that this exponentiation with the within the component densities will not get cancelled with the logarithm, and therefore, if you take the derivative of this with respect to the parameters mu and sigma, they will not separate out, and that is why you need a different way to solve this optimization problem. That is the motivation, so as to why one should move to an algorithm such as the expectation maximization algorithm. Okay. Okay. So, with this we will have to come up with some other way to optimize the log likelihood for mixture densities. So, let us look at what is called as, please remember this motivation, because from now I will talk about a class of families of models which are called latent variable models, okay, of which GMM or any mixture density is a member. A Gaussian mixture density or any mixture model in general is a member of this large family of models called latent variable models. In fact, even transformers and the adversarial networks and variational autoencoders, all of these are latent variable models. It is a broad family of models. I will talk about latent variable models in general, okay, and show that this is a special case, and the algorithm that we construct, which is the EM algorithm, is actually a general class of algorithm that can be applied to any family of latent variable models. Okay, so I will generalize it that way. So, you understood the motivation, right? We wanted to get the parameters of a mixture density, and we could not get it because we have a particular term that will have log of some that is not tractable. So, you need to come up with some other way to do it. So, that is the motivation as far as the ML estimation for mixed density is concerned. So, let us look at these family of models which are called the latent variable models. So, here is the philosophy behind it. See, intelligence or rather information comes through compression. What does this mean? So, there is an idea called information bottleneck. Okay, it comes from the information theoretic standpoint. So, suppose you have your data in some d-dimensional space. Let us say that you can compress all that information in a very lower dimensional space, okay, such that your information content is not reduced. Now, how do you do that? The only way one can compress a large amount of information and put it in a very small space is by understanding the semantics. What do I mean by that? Let me give you an example. Suppose you look at the picture of a human being's face. Now, mathematically speaking, or from a measurement perspective, there are hundreds and thousands of pixels. But how many pixels there are actually semantically useful? Instead of storing the values of each of the individual pixels, you can store information such as, oh, every face has two eyes, they are symmetrically spaced, okay, and there is a nose and it's there, and there are lips which are red and so on. So, if you store a small bit of information and compress it at a semantic level, then everything that you need to know about a human face is known. You do not have to remember each of the individual pixel values or each of the details of everything, right. So, this is the idea of compression. So, if you see, you can think of today's LLM's capability from that way, because think about it. If you want to compress all the information that is there in World Wide Web, which is trillions of tokens of information, into a model that only has billions of parameters, it is compression. See, how do you compress? The only way you can compress is by understanding semantics. Throw away everything that is not important and only remember semantics. That is one way to explain what is happening in today's, I mean, if you take huge amounts of information and try to compress it. Now, that compression has to be put into a modeling framework. How do you express compression in a modeling framework? Is by introducing one other random variable into the system. Okay, so let's look at it. So, we are given some set of data, okay, which is a set, as we know, we have x1, x2 up to xn. So, these are sampled IID from some distribution. Typically, xi is in some RD, right. This is what we saw. What I do is I introduce an additional random variable into the system. So, introduce into the system that is unobserved. What we have observed is the data, right, what we are representing by letter x. Right. Now, we assume that there is another random variable, okay, that is coming from the same sample space, which has not been observed, but that contains lot of information about x. So, it is very well correlated with x, and it contains information about x. So, this is actually called the hidden or latent random variable. It is also called the representation random variable, right, latent space or latent random variable. This is the nomenclature that is used. Let me give you an example. Let us say that we are looking at a data set that contains the pictures of handwritten digits. I am talking about the usual MNIST data set. Now this random variable that I am talking about, okay, let us say that this z typically represented by the letter z, okay. Now this, let us say that this is a 3-dimensional random variable, a continuous random variable. The first dimension of this represents the thickness, okay, of the digit. The second dimension of that represents the symmetry of that particular digit with respect to x axis. It is a switch. So if it is symmetric then it is 1, if it is asymmetric then it is 0. The third dimension may represent if the digit, the written digit actually covers more than 20% of the total pixels. It is a binary value. Does it make sense? Now suppose you have 10 such dimensions, so maybe using only those 10 dimensions, 10 pieces of information, you can actually guess what the digit is, right. If you are looking at, let's another example, let's say you take the example of a data set that contains human faces. One random variable or one dimension of this hidden random variable may be the color of the hair of the person. The other can be, let's say, the gender. So it can be whether somebody is having a spectacle or not. This random variable by definition can be continuous or discrete, does not matter, it is just there in the system, it is not observed, okay. Now why do we introduce this in the system is the question, right. So the thing is, one, for computational ease, we will see that. So one, it will make our computation much easier, but more than that it is for compression. Now suppose you design systems and models where there is access to this particular random variable, okay, then if you can estimate the posterior of this random variable given data, right, then you can actually extract hidden information from data, isn't it? This is another random variable that we have introduced in the system. Now mathematically speaking, since this is another random variable, we can talk of joint distribution. We will see that we will talk of joint distributions between x and z. Because there is a joint distribution, we can also talk of posteriors of z given x. So posterior of z given x will give us hidden information about the data if we can estimate it. Does it make sense? So for instance, let us say that, let us take this example of digits. Now let us say that this hidden random variable represent the semantics of the digits, okay. It is a 10-dimensional random variable, one hot random variable. So one of the values gives you one digit, the second value gives the other digit, and so on. Now suppose you model the system using this latent variable framework and find out the posterior of this z given x. If you can successfully do it, then it will give you what semantics that this data has already, right, without having any labels. Do you understand what I am saying? So that way, it is because of this reason that latent variable models are also used for unsupervised learning. We will see all this in a while. So this is the motivation so as to why one should resort to assuming that there already has that there is already a hidden variable that is there in data which is not observed. Okay. So we will see multiple instantiations of this. Other example is, if you build a language model, in its latent space you can do semantics, in the sense that you have seen this, right. Suppose you give a particular image to these current day AI systems and ask it to change a parts of it. For instance, change the style of the image, right, and erase a particular object and impose some features onto this image and so on. How is this done? It is actually done by doing this. So given an image, they go back to the latent space, and in the latent space they manipulate, because directions in latent space signify semantics, and from latent space they go back to data space again, so that only the semantics are changed and everything is kept the same. That is exactly what is being done. You understand? So start from the data space, project it onto the latent space, manipulate and get back to the data space again. This is exactly what is done in diffusion models, right? Forward diffusion, reverse diffusion. Again, as I said, this is the subject of my next course. But yeah, a diffusion model, which is the state of the art generative model for images, is also a latent variable model. Any questions? So this is very important to understand this philosophy, right? So basically what we are doing is, given data, we are assuming that there exists an unobserved compression space, okay, which is correlated with the data space, and we will estimate that random variable, or we will use that another hidden random variable in our model, in our, while we are modeling our data. So rest is math. So this is the motivation and philosophy. Any questions on this before we move on? Yeah.
What is unobserved? And second is like these values are not known. If we take x, we already have the range space of the random variable, but here we don't.
So the question is, what is unobserved? What is unobserved is this z. The values of z is totally unobserved, right? We only have, as you rightly pointed out, all we have are only the data that we have observed, not the latent variables, the values of latent variables. Now the second question is, how do we use it, right? Is we will, just like we model or we estimate the parameters of the model, we also estimate a distribution over the latent space, as we will see. That is the whole point. Any other question on this?
How do we decide like what semantics are appropriate for a data, or we like decide machine all these?
Again, good question. The question is, how do we decide what semantics are being captured by latent space, right? What semantics is good for a given data? We don't. This is completely unsupervised. We let the model choose whatever it is. So what choices do we have depends upon the model that we are looking at. Some models or some frameworks choose distributional forms for the latent space. Some models choose the dimensionality for the latent space, and every choice that we make has consequences, right? So this is not something that that is given by labeling or anything. This is, we are assuming that there is something hidden in data, and we want to discover that hidden information through modeling. So this is, we have not observed this at all. This is not coming from the data. It is hidden in data, and we want to explore that. We have to unlock it, is what the idea is. Yeah.
Fundamentally, we are not the original narration that we had, that we will estimate densities. This, how does it add to that? Like, how does it? Then, like, what I mean is, the problem remains the same.
Yeah. The question is, does the problem remain the same, that of density estimation? Yes. All we are saying is, in addition to what we have seen as data and an underlying distribution Px here, we have additional random variable that we have not observed, which we will consider while modeling our data. That is it. While we are estimating the underlying density, we will assume that there is another random variable that defines my system.
Which means that for any density, like if we have not gone to this perspective, there will, for every density that we will estimate, there will be existing our latent variable.
That is a modeling choice. See, it is a modeling choice. Do you want to resort to a latent variable model or not, is a modeling choice. But in the case of mixture densities, it comes naturally. As we will see now, a mixture density is a natural choice. I mean, a mixture density can be very naturally represented as a latent variable model, as we will see now. But it is a design choice. That do you want to model your data using a mixture density or not? Okay, but nothing changes. This is only a modeling choice. P theta that we are defining, we are introducing another additional random variable into our system. That's it.
So basically, that hidden random variable, it's some abstract stuff we can't explain, but whatever it is has more info than is more info rich on the actual density than the data samples themselves.
You can say it that way. It is still correlated with the original data. It contains, you can see that as a compressed version of the original data, having information about the original data.
Okay, so whatever noise, I guess, that is present in the data, that will be a bit less or remove, something like that.
Yeah, you can say it that way, but I have not defined what noise is and all that. See, what happens is, as I keep saying, language is too fragile. It fails. Math is what works. So motivation can only take you so far. So as far as mathematics is concerned, we have an underlying random variable, realization and an underlying distribution. We assume that there is one other random variable that we introduce into the system and then model it. Question? Can you be a little louder, please?
What if there are more than one latent variables, like each capturing distinct dimension of size?
Possible. That's again a modeling choice. See, the way to put it is that you make your latent variable has multiple dimensions. It's a vector valued random variable again. So that will capture whatever you just said. Every dimension can be looked into as capturing something different, some different semantic. Yeah.
So do we cap the dimension of the latent variable?
We don't. Typically, it is chosen to be lesser than that of the data variable. In the particular case of a mixture model, latent variable is discrete and it is equal to the number of mixture components that we look at, as we will see now. In the case of mixture densities only, okay. But in the case of, let us say, a transformer, it is taken to be continuous. Again, it's an engineering design choice. See, the mathematical algorithms that we will see now is common through all latent variable models, from mixture densities to transformers. Okay, but the choice that you want to make is model specific.
So two questions. One, are we only estimating P of Z right now, or are we estimating P x Z?
Hold on to that question. I'll write that. So the question is, what do we estimate? We still estimate Px because that's what our interest is, but we do it through estimating what? Huh? No. Yeah, that's one way. The other way to do it is, you represent. I'll write the math right now. Write Px as a marginalization over the joint density between x and z. That's it. That's our model. We'll write that in a while. What's the second question?
It was about like we have sampled xi values, but we don't know.
It is jointly estimated. Yeah.
Since we don't know what this variable is capturing, some abstract thing, coming back to the X-ray example, let's say everything is same, model choice parameters, everything, but the data is different. So we are training the model in a different hospital or different demographics. Do we expect the random this variable to capture?
I don't have an answer to it. Sometimes it would, sometimes it won't. Okay, so the question is, does this random variable, can we interpret what this random variable is, in a sense, right? If it can capture distributional shift or anything, depends. See, 3 and 4 of my PhD students have worked only on this, that's why I have named my lab as representation learning lab. So representation learning is learning this Z, discovering this Z from different modeling perspectives, and it can depending upon what sort of choices you make for the model, right, it will capture different semantics. You can't, it's very hard to pinpoint on what semantics it is capturing.
Is it the same thing? There was this model which was trained on faces to identify whether it's a male or female, and it totally failed when it was tested on the African faces because it was just capturing the presence or absence of makeup.
Yeah, so maybe there is a latent variable that is defined for that, right? So that this model is looking at. You can't. You can only do it post facto, no. So as they say, hindsight is 20/20, because you know that it has already happened, right? So it's always perfect. So hindsight, everything is perfect, but prospectively, but there are algorithms that with which you can sort of regulate what this latent space is going to do. Yeah, that's again, it's out of the scope of this particular course. Okay, but there are ways to do it. Is this clear? So let's look at the math. Okay, yeah. So math is the easier and more well behaved part of it. So we introduce another random variable into the system that is unobserved. It's called the latent variable. So mathematically, for every xi in D, define zi, that is in typically Rk, where k is less than D. This is a typical case, and it need not be the case that the dimensionality of the latent variable is less than that of data variable. It's typically the case because we want to interpret that as compression. Define another random variable with a distribution of its own. Now x and z are assumed to be correlated, statistically correlated. Now this z, which is the latent variable, can be continuous or it can be discrete. Z can be continuous or discrete, I mean it is again a design choice. Okay. Now with this let us define a latent variable model. Okay, with this a latent variable model is defined as, now p theta of x is the model that we are looking at, right, is given by the marginal or the joint distribution between x and z if z is discrete. Okay. So if z is discrete and if z is continuous, define that as the integral. So this is the definition of a latent variable model. Math is so easy, right. So p theta of x, which is the density that we are trying to model, is simply the marginal over the joint densities between x and z, and z is unobserved, right, you integrate the z out. Okay, that is the definition of the latent variable model. Now since we are talking about two random variables here and there exists a joint density, there can also exist the marginals and the posteriors and so on. So there can exist conditionals of this way, there can exist conditionals of this sort, and there can exist the marginal over z, marginal over x and so on, right. All these densities are valid and they exist. Okay. So this is actually a side point, we do not need it here. Now the question is, yeah, there is a question, yeah. The question is, if z is not defined and it is okay, z is not defined, z is unobserved, how do you incorporate this in the model and how do you even talk about the joint distribution between these two, which is a valid question. So as we will see right now, the fundamental foundations of learning a latent variable model is that you not only estimate thetas, but you will also estimate the densities on z. So estimate two things. So far what we have seen is we only estimate the parameters of the underlying density. Here we will not only estimate the parameters of the underlying density, we also estimate the density on z as well. That is how we do it. Okay. We will stop here and continue in the next lecture.